All right, we will get started. I think more people will join in a couple of minutes. Thank you for joining Delhi Rani.
Thank you, sir. Good evening, sir.
Good evening. All right, so before we start, do you want to ask any questions? Do you have any questions? Do you want me to address uh, any questions before we start? All right, I'm guessing you do not have any questions. If you have any questions, again, as usual, you can, use, you can unmute yourself and ask, or you can stop me anytime. You can use chats to do it. So what we will do today is going to be like a revision session. Um, I guess your exams is on coming Saturday, I guess, or Saturday or Sunday, right? So I thought I will quickly revise you what we were studying in this course and quickly give you, probably. I think these class notes are already available in the Google Drive that I usually use to upload the notes. But we will, anyway go through these notes again, and that is what is going to be the agenda. I'm not going to solve any questions. Okay. All right, we will get started. So, this course is about numerical methods. It's one of the important mathematical course that, as an engineer, or even as a physician, people who are doing science or who are doing engineering, everyone should know about it. Okay. I'm sorry. I guess I got disconnected for a while. Sorry about that. So what I was telling is, I hope I'm audible now. Okay. So what I was telling is, as a you know, as a student who's studying both science or engineering, should know a little bit, should know about numerical methods, and it will be useful in various ways, uh, in one way or the other, in his career. So that's why we study numerical methods, and it's one of the important course in every engineering branch. Doesn't matter whether it's a mechanical or aerospace or electrical. Every engineering branch, they do use it. So in this numerical methods, what we are trying to do is, in general, in real systems, we will see different physical systems which will obey certain laws, and those laws can be mathematically expressed, uh, but we won't be able to fully solve those you know solve those mathematical equations, because it will be quite complex. So in order to avoid solving it manually or analytically, in this case, we prefer to use numerical methods, and we make use of computers, and we'll try to solve those equations in the computers, and that is how numerical methods was being used. Okay. So which means numerical methods requires computers, and that's why we started with how a computer knows numbers, and how it stores a number, and because of truncating, or because of you know rounding off certain numbers, what are the errors that is going to happen in our analysis. So that's how we started it. We started with an error analysis. So in a computer, we need to store a number, and let's say if it is a irrational number, something like 1 by 3. Okay, so it cannot store which so this in principle has infinite digits after, or infinite after a decimal point it has infinite digits, but we cannot really store every digit, right, in a computer. So we need to round off at some point. For example, let's say you have a very simple computer which can round off at only up to, it can only calculate up to fourth decimal. Then that error is going to keep, so that is a round off error. And if you keep on doing multiple addition, subtraction, multiplication and division, or basically any arithmetic or logic operations to or just arithmetic operations to these numbers which has already been rounded off, this error terms keeps on building up, and it will lead to a large error in your final answer. So that's why we need to study about errors, and for that we need to know how computer stores the number, and computer usually stores as a floating point numbers. And this is how the floating point representation is. You have plus or minus m, which is called mantissa, and you have you are basically representing it in terms of, in a scientific notation. Okay, so here m is the mantissa, and 10 power k, where k is any integer. Okay, here it is an integer. So mantissa should be between 1 by beta less than or equal to 1 less than or equal to m less than 1. So which means it has to be less than 1, or in this case it should be between 0 and 1. So which means whatever the number, you have to represent it as in between 0 and 1, and the remaining things you will usually store it as 10 power k. Okay, all right, I guess. Okay, so remaining things you will store it as 10 power k. So for example, if you have 5431 as your number, you store it as 0.5431 into 10 power 4, so which is basically 5431. But this is how we store it in the computer. This is called the floating point representation, as floating point representation of a number. And this part is mantissa, and k is the integer, and here it is 4. Okay, if it is negative, again negative is stored separately, and mantissa is again going to be 0.123, and it is you can write it as 0.123 into 10 power 1. So this digits in mantissa is what we call it as significant digits. Okay, so we all studied significant digits, but in a little bit different way in our high school. But here, if you know what is mantissa, whatever the digits you have in mantissa, it's going to be your significant digits. Okay, and you usually truncate after certain finite digits, and so you will have rounding off error in those finite digits. And we saw some rounding off rules. The rounding off rules is something like, let's say if you're rounding off up to second decimal, you will see the third decimal place. If it is above 5, you increase the second decimal place by 1. If it is below 5, you increase the if it is below 5, you will you will just keep the second decimal place as it is. Okay, but only problem is if it is exactly 5, you will see what is the second decimal place. If it is even, you leave it like that. If it is odd, you make it even. Okay, why this happens? Only if you have 5 in your third decimal places, when you are rounding off for 2 decimal places. Okay, so how do you find an error? So we can basically have a relative error. Relative error is nothing but what is the exact error. So for example, using numerical method, you will find a value, but there is an absolute value also, or the exact value. So relative error is nothing but the difference between true value minus the numerical value that you got divided by the true value, and everything is inside what do you call um, everything is an absolute value basically. Okay. This is your relative error, and you multiply with by 100, you will get a percentage error. Truncation error is error resulting due to truncating the higher order terms in your Taylor series expansion. So for example, error resulting from approximating a smooth function by truncating its Taylor series representation to a finite number of terms. So usually any function can be represented as a Taylor series in a Taylor series expansion, right? If you want to evaluate a function at x naught or function at x, by knowing the function value at x naught, you can always represent it as a Taylor series expansion from x naught, right? Now we cannot continuously find each and every term in the Taylor series, so we have to truncate it at some point. And when you truncate it, whatever the remaining terms, whatever the value that the remaining term is going to give is what we call it as truncation error. Okay. And then significant digits, and then we saw more detailed way of explaining for identifying significant digits. If xa is an approximation to x, then we say xa approximates to x to r significant digits, r significant beta digits, if this is satisfied. So it's basically making it more and more general basically. Okay, so you don't need to worry much about this. You should just understand what is significant digits, and if you understand that, you don't need to really remember this formula. Okay, but if you want to, if I want to give an example, let's say x is 1 by 3 and I am approximating it as 0.333, then so what is the approximation to how many significant digits? How do we express that, right? So for that we will write it as x minus xa, and we will write we will find that out to be this is 0.00033. We can write it as this is nothing but less than a half means it's 0.5, so 0.5, so this whole number is less than 0.5 times 10 power minus 3. Okay, so if that is the case, so basically because this formula has 0.5 in it, so we express it like this. So in this case the beta becomes 10 and s minus r plus 1 equal to minus 3. So this will give you r to be 3, which means up to 3 decimal places you are exactly having you have approximated your value. Okay, that is what this means. All right. So if you have any questions in between, or if you want me to explain one more time, you please stop me anywhere or anytime in between. Okay. So that's it. So this number is nothing but it is approximated to 3 significant digits. That is what we are trying to say. That's what we are trying to express in terms of this equation, big equation. Okay. All right. So these are all about the number system. So we understood how the numbers works, how we represent the numbers in a computer or in general. How do we approximate the number? Because we cannot have infinite number of digits while calculating the value. So we understood these numbers. Now we need to apply it for some real systems. So usually in a real system, for example, you will encounter let's say an equations of motion. Let's say you are studying an motion of some body in space. Let's say you are studying about motion of earth around sun or moon around earth. So that can be expressed as a physical equation, and that equation could either be that equation could either be a linear or non-linear equation, and you may be able to solve it. It could be a differential equation, it could be a partial differential equation, it could be an ordinary differential equation, but you may not be able to solve it at some point by hand. So what you do, you try to restructure that equation into you do. So for example, you can discretize that equation, and you can form some linear system of equation. So linear system of equation is nothing but you have multiple variables for which you need to find the solution for. For example, this is the linear system of equation. You have multiple equations and you have multiple unknowns. In this case, you have n equations and n unknowns. Okay, so you have like n equations, and x1, x2, x3 and 2xn are the unknowns. So this system of equation appears after you perform certain operations in your physical equation. So for example, as I said, let's say you want to study the motion of fluid in a pipe, let's say. Now it has its own equation, so like Navier-Stokes equation or energy equation. Let's say you are studying about heat transfer through a pipe, or heat transfer through in your phone, for example. The energy equation is what you solve, or you solve for temperature. You want to see how temperature varies. So when you will have this big complicated equation. Its temperature equation is just one equation. So what you do is that temperature equation you will not be able to solve. So what you do, you basically apply concepts of finite difference method, finite volume method. Although those are not touched in this course, there are certain different methods that you apply to that equation, and that will boil down to system of linear equation or linear system of equations. Okay. Now our ideology here is to solve such complicated system, but our focus is on how do you solve this linear system of equation. Okay, we don't worry about and this set of equations does not just appear only in any engineering, in one of the engineering domain. It is applicable even if you are studying about electric field, even if you are studying about magnetic field, even if you are studying about let's say plasma dynamics, like star formation. All these things will ultimately boil down to a partial differential equations, and you need to study some variable varying along the space. So what you do discretization, you apply finite difference method, all these complicated thing, and at the end all these equation, whichever field you are in, doesn't matter, all these equation boils down to, let's say, linear system of equation. Now if that is what is the problem is, how do you solve it? So that is what we study in the numerical methods. So this is where the linear system of equation is applied. Okay, so here you will have n equations and n unknowns. We typically in your high school, maybe you might have solved like 2 equation and 2 unknowns. You eliminate one of the variable, and then you solve them, right? You find one variable from one equation and substitute them, you find the other variable. So that is the simplest way. Here usually it will not be just 2 equation, it will be like hundreds of equation or thousands of equation or even millions of equation. So if that is the case, we need some general methodology to solve such system of equation, and that is what we first studied. Okay, so in this course, each and every part that we studied is used somewhere in your domain. Okay, that's why this is a common course in any engineering or science program. Okay, so in this case we have linear system of equation, we have n cross n matrix. If that is the case, you can actually express this n equation in terms of Ax equal to B, kind of like a matrix form, in the matrix form. So where A will have these coefficients, A1, A2, A3, these are coefficients which we know beforehand, and B is nothing but your source vector. We call this as a source vector, or in this case it's just a B vector. So B is a vector and A is a matrix. So this big set of system of equation, we are replacing it as a matrix equation, matrix notation as a single, and now the entire system boils down to how do we solve this Ax equal to B. So there are different methods. The first one, first we solve was a direct method. How can direct method is nothing but you have Ax equal to B. You have Ax equal to B. If you just multiply by A inverse, what happens? X is equal to A inverse B. So if you are able to find A inverse, you can just multiply with B and you will find the X. X is what you ultimately want, right? So that is a direct method. How do we directly get the solution vector? The other methods are iterative procedures. So we do not really find A inverse. Instead, we start with an initial X value and we substitute in this equation, and we'll see whether it is matching. If not, we will update the X value. So that is the iterative methods. So in direct methods, we saw Gaussian elimination. Gaussian elimination methodology starts like this. You first take this A matrix and then augment it with B. So we get an augmented matrix. So this will have, let's say, A has n cross n rows, and this will have same n rows, but you will have n plus 1 column. Okay, so it is no more a square matrix, it's a rectangular matrix. And then we do row operations to get a row echelon form. Row echelon form is nothing but your lower diagonal elements, or from the main diagonal elements, whatever is below the main diagonal element, everything will become 0. Everything you are trying to make it 0. Okay, but you cannot directly just put 0 everywhere, so you have to do row operations step by step to reach that value. So that's what we do. We do row operation to get a row echelon form, and then finally, once you get a row echelon form, you can find the last element, last value in that matrix by simply doing back substitution. So from back, you will keep substituting the values whatever we know, and that's why we call back substitution. And we slowly reach the first equation where it has all the unknowns. So that is the overall idea. But what happens is, you will have A matrix, and these all become 0, right? These all become 0, and you have a B matrix. So this one times X equal to this. Okay. So you just take this value to the right hand side, and you will find the final value. And once you find the final value, you substitute that value in the previous value, and that's why we do back substitution. So but while doing so, we do a lot of arithmetic operations, and because of that, we might end up having larger round of errors. Okay, so to avoid that, people use partial pivoting, where in partial pivoting we interchange rows such that elements in the first column are in descending order. Okay, which means so in the first column, you will check the first column and check which one has the lowest number by value, and you will move it down so that you can make that value to be 0, or you can make that to be make it into row echelon form, and then divide the first row with that first element and perform row operations to get the row echelon form, and you repeat the errors, and this will lead to a lower error. And these are all because of the round of errors that we talked about initially. Okay. All right, so this is we can do Gauss elimination. We can do Gauss elimination with partial pivoting. Maybe I can go back to one of our to show you how we did it. Yeah, so basically we try to do Gauss elimination for this in one of our interactions in week 1. So this is what we call it as row echelon form. This is a 3x3 matrix. So as far as your exam is concerned, you don't need to worry. Maximum it will be 3x3. Okay. So this is what we call it as row echelon form. This is a diagonal element, and below this diagonal element, all the elements will be 0. Okay, that's what is called row echelon form. And since you do it like that, for the augmented matrix, you can again divide this augmented matrix, and you can put x, y, z, and this becomes much simpler. So for the last element, you just need to evaluate z, and once you find z, you substitute in this to find y, and you substitute in this to find x. So this is what the backward substitution method is. Okay. Alright, so this is what Gaussian elimination is, and let's move forward. And then we studied something about ill conditioning of the system. So usually if given Ax equal to b, you cannot always solve Ax equal to b. You sometimes you might end up having problems in solving them. So for example, when you have Ax equal to b, for any small changes in your A matrix, you will have large change in your solution. Okay, so I think that also something we saw. If you go up back, so if this is your A matrix, if I change this 1 to 0.001, this is like a small change. Like from if you put 1111, that's one problem. If I put 1.001, which is what I do here, 1.001 here, and this what happens is this will lead to a large changes in the solution value. So if I make it, if you find the solution for this, I didn't really find it here. Okay, I just showed to find condition number. So if instead of 1, if I change it to let's say 2, okay, so compared to the value, if compared to the exact value, this change is very minor. Okay, so if you put 1 and if you solve the equations, and find x and y, and then if you put 1.002 and solve the equations and find x and y, the solution will be very different. Okay, so that is what we call it as. So such systems are called ill conditioned system. It's not well conditioned system. So the easiest way to find out is to find out condition number. If the condition number is very large, then it's an ill conditioned system. For example, for this case, the condition number was around 20,001. So which means it's very high. And for the previous case which I was talking, this one, its condition number was just 20. Okay, it's less. Okay, although 20 is also a very big value, but it is less. Okay, so instead of 1, if you have 2, let's say, that condition number will be low. Okay, so it doesn't really have so it's not just the value that we use here, it's about the changes in the value that we are talking about. So let's say I have 1 here and I have 2 here. Okay, the condition numbers of them will be almost similar, and your solution will change because your A has changed, that is true. But if I have 1.0001 and 1.0012, that will give you a very drastic changes in your solution. So that is something you can try it out. So this is A, right? You can just arbitrarily select a B matrix and solve it and check. Okay. So as I said, we need to find a condition number, and before that we introduce certain norms, matrix norms, and induced matrix norm, and then Euclidean norm, and then finally we saw this condition number. Condition number we can express it in terms of A and A inverse. Okay, max row norm of A or A inverse. So it doesn't really need to be at one of the norm. So here norm of A and norm of A inverse multiplication is what we call it as condition number. So it has to be any of the norm. It can be Euclidean norm, it can be matrix row norm, it can be induced matrix norm, but usually what we use is we use maximum row norm. Okay, I think that's what we did here also, maximum row norm. Okay. Yeah, so this condition number is used to identify whether the system is well conditioned or ill conditioned. If it is ill conditioned, what usually people prefer to do, sometimes we cannot control these values in A, right? So values in A is coming from a physical system, we cannot change the values in A. So what usually people do is they do something called preconditioning. Okay, so basically once you get the A, they pre-multiply that with another matrix called preconditioning matrix, and what that will do is it will not change the physics of the system, but it will change the condition number of this matrix A such that you will not end up having any errors. Okay, so that is called preconditioning of the system. You can read about it in the in textbooks. Okay. Although that is not in your syllabus, I'm just giving you an additional information about it. Um, and the next thing that we saw was LU decomposition. So in LU decomposition for a given matrix, in Gauss elimination we just had a matrix, we augmented it, find the row echelon form, and then we did back substitution. That's the Gauss elimination. In LU decomposition, whatever the given matrix is, instead of augmenting, we decompose this A matrix to L and U. Okay, so that is your first step. We need to decompose this into L and U, where L is a lower triangular matrix and U is a upper triangular matrix, which means lower triangular matrix will have one elements only in the diagonal element and the elements below the diagonal. Okay, so this is what the lower triangular matrix is, and as you guessed, the upper triangular matrix is going to have elements only in the upper diagonal, and all the other elements would be 0. Okay, so and how do we find this coefficients of lower diagonal, or how do you find the elements of lower diagonal matrix and upper diagonal matrix? For that we have this equation. So this equation looks complicated, but if you understand the logic, you no need to really remember this equation. You can just do it on your own. But important thing to note here is when you decompose into lower and upper diagonal, here you have only, let's say it's a 3 cross 3 matrix, here you have only 9 coefficients, but here you have 6 plus 6 coefficient, which is 12. Okay, 6 plus 6 coefficients, so total you have 12 coefficients here, but here you have 9 coefficients. So we need to correlate these two, which means we have 3 more unknowns to find out. So what we do is we try to choose these 3 more unknowns. For example, sometimes what people do, we'll take this as to be 1, 1 and 1. So in this way you have reduced from 12 to 9. Okay, and this side also you have 9 coefficients, so you can basically equate this one, and so this one is nothing but multiplication of this and this, right? So then you can easily equate it. So if you make this 1, so since u1 we already know, we can directly find L1. Okay, and once we know L1, we will try to find out u12. Okay, and then we find out L21, and then we find out u22. So we first find first column of L and then first row of U. So first column of L and first column of L, and then we'll find first row of U, and then second column of L, and then we'll find second row of U, and then third column of L and third row of U. Okay, so that is the methodology that we usually follow. So the whole idea is to decompose A into L and U, and once you decompose, you can write this Ux to be Z, so it becomes Lz equal to B, and since L is a lower triangle matrix, you can actually do forward substitution, and since U is an upper triangular matrix, you can do backward substitution. So you just do forward and backward substitution. Okay, and that is the way. So once you find Z from, so L and B we know, so you do the forward substitution to find Z, and then substitute the Z here, and U is a upper triangular matrix, so you do backward substitution to find X. So that is how you get the X value. And this LU decomposition actually requires more operations to be done and than Gauss elimination. So usually if you have only one system to be solved, you usually prefer to go with Gauss elimination. But LU decomposition become very beneficial when your A matrix does not change. For example, you might end up having some scenario such that you will have AX equal to B1 and AX equal to B2 and AX equal to B3. So you will end up having like 3 set of linear system of equation to be solved for. Okay, you can write x1, x2 and x3. So I need to solve for x1, x2 and x3. All these are vectors. Okay, all these are vectors. Now but what is common is you have A matrix to be common for all 3. So since you have A matrix to be common, you use LU decomposition once to find L and U, and use that same L and U for all the three system of equation. So if that is the case, when you have, then the number of operations that you do will boil down to very low value compared to doing Gauss elimination and again for three different set of equation. So basically Gauss elimination, how will you do? You will do A1, sorry, not A1. You will do AB1 augmented matrix. You will do row echelon form and then find X1, and then again you have to do row operations to eliminate this matrix, right? So instead of doing such big calculations, what people usually do is they just do LU decomposition for A, and you just change the B matrix, and you change the B matrix to find Z, and then using Z you find X. As simple as that. Okay. This can also be used for inverse of matrix, and inverse of matrix is nothing but something like this, and then so only for this to be done, it has to be a positive definite matrix, which means you will have X transpose AX should always be greater than 0. Okay, so positive definite matrix is invertible, which means you can invert that matrix, and all eigenvalues and corresponding eigenvectors are positive, and all diagonal entries are positive, and each diagonal entry is greater than the sum of absolute values of all the other entries in corresponding row or column. Okay. Alright, so this is about positive definite matrix, and finally there is also one more direct method, Cholesky method. That only works if your matrix is symmetric and positive definite. Basically you will write A to be L transpose or U transpose. So once you find L matrix, you can perform these operations and you can find the value. Okay. Alright, so these are all direct methods, and then we studied iterative methods. The reason to study iterative methods is with direct methods what you have is your number of computations keeps increasing with the increase in the system. So for example, when you go from 100 to 1000, your number of operations will keep on increasing. So in iterative methods you can quickly reach the solution value without doing that much operations. That's why iterative methods is usually people prefer in solving any linear system of equation. Okay, so and it's also useful for only for square systems, and that's usually how that is how all the physical systems behave. We rarely see rectangular matrix. Okay, so can be used only for square systems and good for large and sparse matrix. Okay, so basically we try to start with some xk, and we find the new xk from this kind of method, which we call it as an iterative function. Okay, and for example, let's begin with Jacobi method. The Jacobi method will have this A matrix, you can write it as L, D and U, where this is not the LU matrix that you see in the LU decomposition. This is like you just separated the coefficients, that's all. L plus D plus U. Okay, it's not A is equal to L plus D plus U. It is not LU. Okay, so this is not. So if that is the case, then you can write this iterative function something like this. So basically L and U I am going to multiply with X, but from the previous iteration value, and I am just taking it on the other side, and D times X k plus 1, which is the new iteration value, is what I am trying to get it. So X at new iteration value is minus D inverse L plus U X k D inverse B. Okay, this is the iteration matrix and this is the Q. So in this case what we do is, when we will the xk remains constant when we find xk plus 1, remains constant in the sense we do not update xk value. But in Gauss-Seidel method, whenever we get a new xk's in each and every vector we have n x's, right? So when you get a new value of one of those x's, we will try to apply we will try to update these value in the upcoming uh, you know equations. Okay, that's the Gauss-Seidel method. um, so basically, for example, in a 3 cross 3 matrix you have xk plus 1 xk. So for while calculating x1, we don't know x2 and x2 as a new value, but while calculating x2 we know the newer value of x1, so we use that here. In Gauss-Jacobi we don't do that, this will be still xk. Okay, that's the difference between Gauss-Seidel and Gauss-Jacobi. And the other one is successive over relaxation method. Nothing but here, when we are using this new value, instead of directly taking the new value, I will weight some with a new value and some with an old value. So that's what the successive over relaxation method. So it's like in between Gauss-Jacobi and you know Gauss-Seidel. Okay. So that's what, if you put W to be 0, it's Gauss-Jacobi, and W to be 1, it becomes Gauss-Seidel. So basically your iteration matrix remains the same. Okay. You don't need to really know all these derivations, but if you know how to do Gauss-Seidel and Gauss-Jacobi, that is fine. All right. So if this W is greater than 1, we call it over relaxation, which means we are trying to accelerate the convergence to that value. But if it is less than 1, we are slowing down. So that's why we call it as under relaxation. And the optimal value is optimal value that could be used to quickly reach the solution is based on the spectral radius of the Jacobian iteration matrix. Okay. All right. And then so since these are iterations, when to stop the iteration is the question, and for that we studied about convergence. Convergence is nothing but when a couple of iterations does not vary your solution, which means it's not going to vary anymore even if you do some more iterations, right? So which means it has achieved an convergence. So we just check whether the previous iteration value and then current iteration value is almost same. Okay. And if you want to do it more rigorously, we know the real solution vector, and so the error term becomes xi minus xs. And if the error term, if the error at ek plus 1 is less than error at ek, which means solution is going to converge, which means error is continuously decreasing. Okay. And the sufficient condition for convergence is this P matrix should have its norm to be less than 1. Okay. All right. So that is one thing. And if every eigenvalue of P satisfies this, the spectral radius becomes this. These are all just giving the necessary and sufficient condition for convergence. I will leave it up to you to revise this. One important thing is, if you have an iterative solvers, if your matrix is diagonally dominant, then it definitely can guarantee convergence. Diagonally dominant in the sense, if your diagonal elements are much larger than sum of absolute values of all the other elements in the row, okay, in that particular row, if that is satisfied, then that system can guarantee convergence. Okay. So you should always choose a system in such a way that diagonally dominant matrices you can observe. Alright, so that is all about this linear system of equations. So for a given physical problem, we will construct this linear system of equation, and that linear system of equation can be solved using different methods. One was direct method, one was other set of methods are iterative methods. Okay. So that is one class of problems that we deal in numerical methods. The other things are non-linear equations. So sometimes if it's a linear equation you can solve it, but if it is a non-linear equation, it becomes difficult for us to solve the problem. So and it's also, you cannot do it analytically basically. Okay. Just give me a minute, I will be back. Sorry about the sorry about the disturbance. So the next thing is nonlinear equation. As I said, we will linear equations are easy to solve, but nonlinear equations sometimes will become difficult to get solved, and that's why we do different numerical methodologies to get the solution. So when we say nonlinear equations or nonlinear functions, it will have product of variables, that is some, if you see a product of variables, that is a nonlinear equation. Or if you see non-algebraic functions, for example trigonometric functions, exponential functions, or hyperbolic functions, those functions, if those exist in your equation, then it becomes we call this as transcendental functions. If those functions exist in your equation, then that functions are called, that exists in your functions, then they are called nonlinear functions. And when you have nonlinear functions, you do not have a closed form solution to such problems. Okay, so usually when we are trying to solve a function, what we are doing is we are trying to find the root of that function, which means when the function becomes 0, or for which independent variable, for which number of independent variable the function becomes 0, right? So that is what we call it as roots. And convergence, as I said, we will see about how to, we will check how the iterative values are changing from previous iteration to next iteration, and if that is of order of some p, then that is called order of convergence. Okay. So first method that we saw was bisection method. In bisection method, we use a intermediate value theorem, and we basically make sure the root lies between these two, between two uh, limits, and we'll try to guess a value in between. And so if this is the two limits, we will try to find the midpoint of it, and we'll see whether the root lies between the first limit and the midpoint, or the second limit and the midpoint. So that is what we do. So for that, we evaluate the function. We will equate that to, if it is equal to 0 for that midpoint, then your midpoint is the root. If it is if the multiplication of f of a and cn is less than 0, then it is between a and c. If it is greater than 0, then it is between b and c. Okay, where b is the later limit and a is the first limit. Okay, but we cannot actually converge to that exact value. So what we do, we will try to see whether the value is somewhere near the root. Okay, so that is what we mean as convergence. We'll see whether the root is nearby. Okay. So this bisection method is very easy, and it always converges provided you have a root between these two intervals. And but it is relatively very slow to converge. It can take n number of iterations to converge. So that's why people go with regular different methods. One of the other method is regular falsy method, where you try to draw a line between these intervals a and b, and see wherever the line crosses the x-axis. You will check whether that point is whether that point and the other point, where exactly, which section exactly contains the root, whether this section or this section, and based on that you will one second. Oh, shit. Yeah, okay. I think there was some network issue I am facing. All right. So where we stopped was this. Dividing this instead of taking midpoint, we can always do a much simpler approach. Where not simpler approach, but we can take a very unique approach such that instead of you know randomly choosing midpoint, we can choose in such a way that just give me a minute. So we can always choose in a way such that we have such that our so the interval that we choose, we can choose in such a way that it is closer to the root basically. So that is what we do in regular falsy secant method. Secant method, we draw a line, find P0, P2, and then we will try to uh, you know apply this logic, and then finally we will get this way. So these are all one way. It's just once given an interval within the in between root x's, then you can use this. The most efficient way is to use Newton-Raphson method. The Newton-Raphson method uses the function and its derivative. Okay, so this is a simplified iterative function that you need to choose. Xn plus 1 is nothing but the next iteration's value, or this iteration value. Xn is the previous iteration value, and you evaluate the function using the previous iteration value and evaluate its derivatives using the previous iteration value, and substitute in this, you will get a next iteration value, and you continue this until convergence. But only problem with Newton-Raphson is it does not guarantee convergence like a bisection method. Okay, so that is the only problem. And near zero, it can also diverge. Okay, so if f of x has no real root, the iterations may simply oscillate. That also will happen, and sometimes it does not converge. All these things can happen, but the order of convergence is second order, which means it will quickly converge. That's it. Okay, and the next one is a fixed point iteration, where fixed point of some other function is actually the root of function f of x. Okay, so f of x equal to 0 is whose root that we need to find out is actually a fixed point of g of x. So you have to select a g of x, find its fixed point, and use it as a root. Okay, so g of x should belong to the domain g in between a and b, in between that is the limit in between. We are trying to find the root, and g of x is continuous, and the iterative function g of x is differentiable. Okay, so g of x equal to x is whatever satisfies g of x equal to x is what we call it as fixed point. Whatever the x satisfies g of x equal to x is called as fixed point. So now, assuming g of x is continuously differentiable, we can have lambda to be like this, and x of g of x has a unique solution for x of star, and then, as I said, you first choose a g of x, and then you iterate it and get a fixed point for it, and that would be your root of f of x. Alright, so these are all nonlinear equations. Now if we have system of nonlinear equations, if we have multiple nonlinear equations which we need to solve it together, like system of linear equation we had, now we have system of nonlinear equation. If that is the case, then again you can write it, you can do a Newton-Raphson method, but to find a Newton-Raphson method you need something called Jacobian matrix, and where the Jacobian matrix is nothing but this is how you can express Jacobian matrix, which is dou fi by dou xj, where fi is the ith function and xj is the jth uh, you know unknown jth variable that we are trying to find out. For example, f is a function of x1 x2 to xn, and we have n, so we have n functions and n unknowns. Okay. Alright, so that is about Newton-Raphson method, and then you instead of this division by f dash of x, we have what we have is we have Jacobian inverse. So Jacobian is nothing but your differential here. Okay, but in general we can either do this Jacobian inverse, or we learned linear system of equations. So based on that you can actually, instead of taking Jacobian, we can actually find this delta x by solving this linear system of equation, and that delta x you can add it to the previous iteration value to get the new iteration value. That is also one method, and the same fixed point method that we studied for the single nonlinear equation can be extended for multiple nonlinear equation. Okay. So the best choice of g of x will be the fixed point method. Will give fixed point method same as Newton-Raphson method. Okay. So these are all about solving nonlinear equation, and then now we will be so now at some point you may need to find eigenvalues and eigenvectors of some of the matrices that has been given to you. So to find out, you can use different methodologies. That's what we studied, and before that we know what is a characteristic polynomial mean for this. You just take a minus lambda I. We know how to find eigenvalues and eigenvectors. There's no problem in that, but we know only for 3 cross 3 matrix. We did it only for 3 cross 3 and 2 cross 2 matrices max, right? But in general, if the matrix is very big, you need to follow certain methodologies. So there are certain terminologies such as characteristic polynomial we already know. So and then algebraic and geometric multiplicities is there. Algebraic multiplicity is the number of times the root of characteristic equation is repeated, and geometric multiplication is the number of linearly independent eigenvectors you have for a given corresponding lambda. Okay, and then there are some properties you can go through, and diagonalization in the sense, once you find eigenvector matrix, if you can represent your A matrix in terms of eigenvector matrix and an eigenvalue matrix, so that is what we call it as diagonalization. So where P matrix is eigenvector matrix and P inverse and multiplied by D in between, where D is a diagonal matrix where each diagonal element have eigenvalues of the matrix. Okay. Now it is very useful when you decompose your A matrix in terms of P and D, because if you want to find A power any m, it is going to be simply P D power m and P inverse, where D power m you can easily find out because it has only diagonal entries, and if D power m is nothing but all those diagonal entries you find to the power n. Okay, that is what this D power n is. So that is the advantage of doing diagonalization. You can easily find any order of A. And similarity transformation, it's to transform a matrix from one space to the other space. Okay, so here we say being them similar. Okay, so here you can pre-multiply by P inverse, where P inverse could be your eigenvector matrix, and A and P inverse AP are similar, and transformation from A to PAP is similarity transformation, we say. Okay, this reduces the complexity of problem by evaluating eigenvalues. There exists a unitary matrix which you can write it like this, and then certain other matrix you can go through, and then we have Jordan canonical form. We study Jordan canonical form of a matrix, where you express this big matrix in terms of smaller Jordans. Okay. Um, and then A is diagonalizable if and only if the size of Jordan block is 1 and non-definite. So that is the point of this. And finally, if you do not have square matrix, if you have rectangular matrix, then we won't be able to do this decomposition. So that's why there is some other principle called singular value decomposition, where you decompose it in terms of U, S, and V. It's also basically SVD decomposition, um, and and the corresponding dimensions you need to take care. Okay, and then we also saw Greshkorin theorem. This is useful when you have a preconditioning matrix, when you want to construct a preconditioning matrix, especially for a nil condition system. So this Greshkorin disk keeps reducing. This will give you an idea of where the eigenvalues lies, and if your matrix is well conditioned, it can Greshkorin circle to find the eigenvalue can evaluate the choice of P. Okay. So union of all Greshkorin disks is where the eigenvalue lies. All right, and then so all these things we are studying because to find an eigenvalue. So the first method is the Jacobi's method. So in Jacobi's method, it's also an iterative method to determine eigenvalue and eigenvector, and we do it by applying series of rotational transformation. Okay. So for example, this is your J matrix, and this is your rotational orthogonal matrix, and what you do is you multiply by J transpose and J, and you will so this transform matrix will be similar to the A matrix, so that will not change your eigenvalue, just the numbers in your matrix will change. So we continue to repeat this continuously until our off diagonal elements are 0, and finally we end up having diagonal matrix, and that diagonal matrix will have diagonal elements which are basically your eigenvalues. That is how we do Jacobi's method to do this. But problem is you have to keep multiplying matrix again and again, so it's a time consuming when you particularly have very large matrix like thousands of rows and columns in there. And this is also applicable only for a symmetric matrix. So that is the disadvantage of Jacobi method, but it is easier. So you just construct a rotational matrix and then this orthogonal matrix. For that you need to find theta, and that theta can be found using this value. So you find the largest off diagonal element, you use these values to find theta, and using theta you construct this matrix, and you multiply both sides of this A to get another matrix, and you repeat this process again and again until your matrix becomes diagonal. Okay. But since it's a time consuming, we also explored the other method, which is a power method, and there's also another method called inverse power method. So in power method should have only one dominant eigenvalue, that is one of the condition, and should have n linearly independent eigenvectors. So basically we know, so why it's like an iterative procedure. We choose an initial vector v of 0 and we multiply with a, and that will give you y, and you find the largest value of y, divide the entire y by that largest element, and that will give you your new eigenvector. So you continue it again until you reach convergence basically. So the continue it till lambda of k plus 1, where lambda is nothing but your largest element that you chose to divide, right? That is your lambda. That's lambda is the eigenvalue, and your vector is nothing but your eigenvector. So until this eigenvalue does not change much, if it is less than a tolerance value, you stop there once it is less, and that will be your eigenvalue and eigenvector. It's much simpler. You don't need to think a lot. You just need to choose a better initial guess. If you choose a wrong initial guess, or there's no such thing called right or wrong. If you choose a very you know like very distant initial guesses, it will take a larger iteration to converge. That's the thing. Okay. Now, um, so so if you want to find more eigenvalues, like this will give you dominant eigenvalue. If you want to find a more eigenvalue, you do a transformation. The transformation is that you change, you take the matrix, you subtract this eigenvalue times u and u transpose, where u is something like this, and that the resultant matrix will make the dominant eigenvalue to be 0, which means the next dominant eigenvalue you can find by the same power method. So you repeat it this entire power method again until you find all the eigenvalues. Okay. So there are some disadvantages. It's as I said, the speed of convergence also matters, because if it is very distant, then you can quickly converge. If the lambda 1 lambda 2s are different eigenvalues, if the lambda 1 lambda 2 are very nearby to each other, it will take a lot of time to converge. Okay, and then there is a shifted inverse power method. It's also similar methodology. I think I will just skip in the interest of time. So only thing is, what we have is, instead of just simply doing this iteration, we introduce additional terms, like you have alpha I. Okay, so that is this alpha. You will if you vary that alpha also again, then it becomes a different method. And if you choose alpha to be alpha, if you choose to calculate it like this, then you call it Rayleigh quotient. That's the thing. And the inverse power method is nothing but is to find the smallest eigenvalue. Power method is to find largest eigenvalue, dominant eigenvalue. Inverse power method is to find smallest eigenvalue, and that you will do it by taking that by exploiting one of the property of a matrix, square matrix, that is, the smallest eigenvalue of A is nothing but the dominant eigenvalue of A inverse. So that's the it's just you are using A inverse to find the eigenvalue. That's all. That's we call it inverse power method. Okay, and in these cases, as I said, this LU decomposition will be beneficial, because your A matrix does not change. Only your V matrix, V vector, keeps on changing. So in this case, you can write A as a LU, and you can easily quickly solve these things. Okay. So this is all about solving matrices, finding eigenvalues, and solving nonlinear equations. And then we went into interpolation. The interpolation is nothing but, for given set of, we will be given some tabular values, and we will be asked to find the function values somewhere in between. Okay, so if that is the case, how do I find the function values in between those tabular values? Okay. For that, we use something called Weierstrass theorem. I'm not going to get into details of it. I'm just going to touch briefly about the important parts. So the first thing we saw is linear interpolation. That is, usually we do whenever a table is given. Okay, this we have two x's and we have function in between, some number is given, so we linearly weight these two functions to get the linear interpolation value. You can also extend that to quadratic interpolation. Basically, what you're trying to do is, between these 2 points, you are trying to fit a quadratic function to get the value. So for quadratic interpolation, you need additional one more value, x2 also, to find out. Okay. For linear interpolation, you need only 2. For quadratic interpolation, you need 3. And similarly, you can also increase it as much higher orders as possible. The method of interpolation can be usually divided into either equally spaced or unequally spaced. For equally spaced, we use Newton's and Gauss method, and for unequally spaced, we use Lagrange and Newton divided difference method. So and we introduce certain finite difference operators. I think these are all quite straightforward: forward, backward, central, average, shift operator, and the differential operator. And basically you can write each operator in terms of other operators. That also we know. Okay, so basically this one is what I'm talking. This is a shift operator. Shift operator can also be written in terms of forward operator. It can be written in terms of different other operators. So, so basically the forward difference method is to find the forward first. Whenever some tabular values is given, you first, if you are going to apply forward difference, you will first construct forward difference table. So for forward difference method, you we can use forward difference method only if the value that you are seeking for is in the initial values, initial some um, some, whether if that value lies in the initial set of table, like initial part of the table, then you can apply forward difference. If it lies in the later part of the table, then you can apply backward difference. It doesn't it I mean, you're not restricted to apply just forward difference or backward difference, but it would be better if you apply forward difference to get a better interpolation value. Okay, so forward difference is nothing but, I mean, you apply, you know construct this table. You just need to find difference. So this is, so this value would be y1 minus y0, y2 minus y1, and then you continue doing it until you as much as possible. And then for Newton's forward difference, this is your formula. You just substitute your del y naught is what you will find, right? Del y naught, del 2 y naught, del 3 y naught, del 4 y naught. All these things you substitute in your Newton's forward difference formula. You will end up having the xp value of xp you are seeking for. And for forward difference, your p should lie between 0 and 1. So for example, where this p comes in is what you are going to choose as x0 and x1. So although this says x0 x1, it depends upon what is the value you are seeking for. Let's say your xp lies somewhere in here, then your x0 becomes this, x1 becomes this, x3, x2 becomes this, x3 becomes this. Okay, only if this is satisfied, then your p will be between 0 and 1. So you need to update your equation in that way. Okay, and same goes to Newton backward difference. So here you will have a p minus, and here you will have p plus 1, and then the error of approximation. So basically we have a polynomial, we have approximated it. Basically what we are trying to do is, this is a polynomial, we are trying to approximate between these values, and but the real value will also have additional error. So that's what this error is. This is p of x, this is r of x. So the real value is this polynomial x that polynomial p of x is what we can get, and r of x is the error, and we can express it something like this. I'm not going to get into details. And then there's also something called extrapolation. If you are trying to find a value that is outside this table, then we call it as extrapolation. Okay, so for that you can construct the polynomial for the full table, and then you assume that polynomial will be applicable outside this table also, and then you just substitute the x value in that polynomial to get the extrapolation value. Okay, and then the central difference table, the forward, backward. So each of this interpolation formula have its own they have their own formulas. You just based on the question, you just apply different formulas. For everything you construct the table first. Okay, likewise Stirling's formula, Bessel's formula, all these things. And the next part is the Lagrange interpolation formula, where Lagrange interpolation formula is typically you will use it when you have unequally spaced tabular points, data points. So you no need to have equally spaced data points. Whatever we saw Newton and Gauss method, you need to have equally spaced data points. For Lagrange interpolation formula, you have this Lagrange coefficients. So nothing but, again the same thing, polynomial, but the polynomial is Lagrange coefficient multiplied by that function value. So L0, L1, L2, and you continue with till Ln. How much ever data points that you have based on that, and each Lagrange coefficient can be expressed something like this. Okay, so you find this Lagrange coefficient is just the differences in x values. So you find this Lagrange coefficient, you already know f of x naught, f of x1, it's already given, x naught, x1 are given. So based on this you can construct this Lagrange polynomial, and using this polynomial you can evaluate any value in between. Okay. Similarly, there is also the next method is Newton's divided difference method. So basically you find divided difference for each and every data point, and then you finally have this function. This is the final polynomial function. You substitute those divided differences here, you will end up and then you substitute whatever the x you want to find out to find the function value. Okay. And we also saw Hermite's interpolation. In Hermite's interpolation, in addition to function value, you also use derivative of that function value. So this yi also additionally comes. That's the difference. Okay. So these are all for interpolation, but these methods can also be applied to when you want to find when you want to do numerically differentiate. So for example, if some tabular points are given and you know these are the function values, but I want to know derivative of these function values, okay, then in those cases also you can find out, you can use these methodologies. For example, you can start with Newton's forward interpolating polynomial. You construct the polynomial, and so this is the polynomial that represents the function, best represents the function. Now what you do, you differentiate this polynomial, you will end up having numerical differentiation. You will end up having the derivative of this function. You evaluate the derivative at any point that you want. That will be your final solution. Okay. So you can either construct and then differentiate, or we can do it symbolically, and we can write dy by dx is, you need to follow this formula basically. So you will have, anyway you have to construct forward difference table. Once you construct forward difference table, you can directly apply in this formula to find dy by dx, or you actually can apply this formula to find y and differentiate them. That is also fine. Okay. So this is dy by dx. Similarly, if you differentiate this, you will end up having d square y by dx. Okay. Now this is for Newton forward. Same you can do for Newton backward, you can do for Lagrange, you can do for Newton divided difference. Every method, that every interpolation that we did, we can extend the same thing to find numerical differentiation. Okay. And finally we also studied parallelly errors, how the errors propagates. I'm not going to go into detail. Stirling's formula and Bessel's formula we can apply. All these things are fine. And finally the method of undetermined coefficients. So this comes when you want some freedom in choosing the tabular points. So for example, if we know that the function at this value is going to depend on 2-3 values before that. Let's say we have some idea that this function is going to depend on 3 values before and 1 value above. I want to construct only polynomial using these 3 values to best represent that function. So instead of thinking about it and constructing the whole polynomial, if we know some physics of that problem and we say, see, this is the point I want, and if this point will behave only mostly based on the previous 2 points and the first point, or it always behaves based on only previous points, not the points in front of this. Okay. When you have that kind of idea about your physical system, then you can go with method of undetermined coefficients, where you choose this as your stencil, like I want this value to be found between the previous points, and express each of these previous points in terms of Taylor series expansion, and compare this Taylor series expansion with this polynomial and the coefficients you can find from the Taylor series expansion. And that is how we found when you want f0, f1 and f3 instead of f2, let's say it does not depend on f2, then your derivative will become something like this. Similarly, you can do second order and first order, second order derivatives. Okay. So this is how you do numerical differentiation. Once you get the polynomial, you can differentiate. That's the whole point. And then the next part is numerical integration. So here sometimes we won't be able to do integration. So again, we will, for a given function, you evaluate those function at different set of points, okay, and then you construct a polynomial, and polynomial can be easily integrated. So that's what we did here. So initially we can do something like Lagrange polynomial, uh, and you can integrate that Lagrange polynomial, or in this case you just need to integrate the Lagrange coefficient. You will end up having the integral. That is one way. The similarly we can also do for Newton's forward difference, and that would make you construct the polynomial, and instead of this function you replace the polynomial. And since you know the polynomial, you have to just if you substitute this value, it just becomes a function of p. Okay, p is nothing but x minus x, p by h, okay, or x minus x naught by h. Okay, that is Newton's forward difference. You can also do for Newton backward difference, that's no problem. The other rule is rectangular rule. For example, if they have given you x naught and f of x, so all these requires you to construct a polynomial and integrate. And but you can, what you can also do is, without constructing the polynomial, if this function, if these tabular points are given, if I want to directly find the integrand, then I can go with rectangular rule, other quadrature rule. There is also trapezoidal rule, Simpson 1/3, Simpson 3/8. All these rules we can go forward with. Okay, so this is your function, and your x naught and f is given at each and every point. This these values are given, but we don't know how exactly it varies in between, and x's are given. So what you do, we just assume this is a rectangles. These are rectangles. Okay, and rectangles are easy to evaluate. What is the area? So basically, when the integral is nothing but the area under this curve, right? Area bounded by this curve and the x-axis between the interval a and b. So we just assume that these are rectangles, then it becomes a rectangle rule. Or you can also assume that these are trapezoids, then it becomes a trapezoid rule. So trapezoid rule is much more accurate than a rectangle rule. Okay. Then there is this quadrature rule. Quadrature rule, what it tells is, we just substitutes, it just takes into account of some weights, and you have this Newton Cotes quadrature formula, and that weight is nothing but, in this you can also express it as a trapezoid rule. So all these trapezoidal rule, all the other rules, it's going to come as a Newton Cotes quadrature formula. So it's a more general way of expressing all these rules. Okay, so the first rule that we saw was this trapezoidal rule. This trapezoidal rule, you just if it is like from a to b is given and some function is given, you can just make this as a big trapezoid, and you can find this area. That is trapezoidal rule. Or to have a more accurate finding of integral, you divide this into multiple small portions, and make each of these portions as it apply trapezoidal rule to it. Then that becomes a composite trapezoid rule. Okay, that is what a composite trapezoid rule is. So this is how the final formula looks like. You have this initial point, you have the final function value, all the inner function values are multiplied by 2. So that is trapezoidal rule. In Simpson's 1/3 rule, you take 3 of the point, approximate it as a parabola. Okay, that is what we do in Simpson's 1/3 rule. Approximate it as a parabola of degree 2, and the final Simpson 1/3 rule would look something like this. And if you are dividing it as a multiple points, then you can express it as a composite Simpson 1/3 rule. For that, you have initial function value and minus like last function value, and the odd values are clubbed together, odd functional values are clubbed together and multiplied by 4, and the even functional values are clubbed together and multiplied with 2. Okay, and these have you can say these have higher order of accuracy. Okay, in trapezoidal rule you have like second degree, second derivative, second order, and this becomes like a fourth order Simpson rule. Okay, so which means Simpson rule is more accurate. Similarly, Simpson 3 by 8 rule. Simpson 3 by 8 rule basically uses 4 nodal points, and you can approximate it as a cubic polynomial. And the other one is, but still it's a fourth order accurate. I mean the leading error term is fourth order, which means third order accurate. Um, and But this can be applied only if you have uh, intervals in multiples of 3, and this can be applied only if you have intervals, even number of intervals. If you have odd number of intervals, we cannot apply. Okay. All right, similarly we can do composite Simpson's 3 by 8 rule, and then finally Gauss-Legendre integration rule you can do. So you have 1 point rule, you also have 2 point rule, 3 point rule. You can actually construct number of rules using this. So basically we are trying to approximate this as some lambda times function of x. If you want to use, let's say, 2 point rule, then we use 2 of this function, if lambda 1 and lambda 2, and we will say this function will be accurate for 1 and x, that is the difference. And if you have 3 or 4 point rule, you will take like 1 x, x square and x cube. Okay, so how many functions that you want it to be accurate, is that's what determines these different rules. So for example, in 2 point rule we want to make this exact for 1 x, x square and x cube, because you have like 4 unknowns, so you need 4 functions. If it's a 3 point rule, you have 6 unknowns, so you need to have 6 functions that it has to exactly match. If it is exactly matches, then you equate them, you will end up having the rule, 4 point rule, 3 point rule, all these things. But this is applicable only if you have intervals between only if you have integral between -1 to 1. So that is the whole point. If it is for a general interval from a to b, then you have to transform this function, and that transformation you can do it by using this. Okay, and that is how you do numerical integration. And finally, what we saw in this course is ordinary differential equation. How do we solve ordinary differential equation? So basically we classified it as a linear and non-linear ODEs, but here the non-linear ODEs, here the linear ODEs can actually have non-linear functions in it. Okay, the functions can be non-linear, but as an ODE it could be linear. Okay, but in here the non-linearity, in the sense, if your independent variable, if your dependent variable is in product of another dependent variable, or if it is inside let's say if it is in the product of derivatives of those variables, then we call it non-linearity. Okay, although we didn't study much about non-linear ODEs, we also classified it as an initial value problem and final value problem. Initial value problem, we know only initial conditions. Initial conditions are always specified at a certain point. In a final boundary value problem, you have more than one condition specified, so the solution domain is bounded. So if this is your dy by dx and this is your function, then you can if it is an higher order derivative, then you can replace it with a system of first order ODE. That will help you in that will help you in solving the problem. Okay, so to begin with, we started with different numerical methods to solve a ODE, and first one was Picard's successive approximation method, where it's a semi-analytical method. You have to evaluate this function and integrate this function, and you need to do it in iterations. And the next one was Euler's method. Euler's method is nothing but first order approximate from the Taylor series, right? So it's also an iterative method. Your yi plus 1 is nothing but your yi plus step size times function of xi and yi. Okay, so Um, so from Taylor series we can say this is at a lower order accurate. So we go with the higher order accurate methods. Those are quadratic Taylor methods, where you use additional one more equation from the one more term from the Taylor series, where it is h square y double prime k, and the higher order also you can express it something like this. Okay, so these yk, y dash of k, y double dash of k, you need to find out for uh, each and every step. Okay, and then we discuss Euler's modified method. Euler's modified method is nothing but you have Euler method, and using Euler method we predict some value, and using the predicted value we will correct that value by an additional step called corrector step. Okay, that is what we call it as Euler modified method, and this is also called RK2 method, Runge-Kutta method. So in general, Runge-Kutta method, what you will have is you are just trying to express this y to be y naught plus k, and this k can be omega 1 k1 to m number of orders, and this case can be expressed as like this. But for this you need to know what are these omega 1s, omega 2, and also this alpha 1 beta 1s and all. So you can use Taylor series expansion to do it, and if you will not have enough number of equations to do it, so some things you will arbitrarily choose some of the variables. So when you have different number of different set of case, you will end up having different RK methods. Okay, so that is what the initial is RK2 method, where you choose omega 1 and omega 2 to be off, and alpha 1 to be 1 and beta 1 to be 1. Okay, similarly you can also do RK4 method, which is widely used everywhere. People use RK4 method, and this is also kind of like you have multiple predictions and a correction, but in addition to prediction you also take a half step, x naught plus h. Okay, those are the different methods, and these methods require you to find, requires only one requires the functional values at one step, right? But you can also extend it to multiple steps. So since I'm going to predict the next step, I have the information of multiple steps behind me, so I can use all those steps values. Then that becomes a multi-step method, where one of them is Milne's predictor method, where you have predictor and corrector equations or something like this. But this requires y n minus 3, n minus 2, n minus 1 and n. So this not just requires yn, it also requires n minus 1, n minus 2 and n minus 3. So 3 more additional steps you need. So these methods have a starting problem. So initially you cannot start from y of 0 equal to some value, and you cannot start from there. So initial 3 steps you need to use like RK4 method or Euler method or something, and later you can use Milne's predictor corrector method, and these are all having you can see y power 5, like fifth order, which means it's all like order 4 accurate. Okay, all right. So this is where we stop. So we briefly touched about ordinary differential equations. It does not really stop here. After this you will also have partial differential equations, how to solve them here, and also if you have nonlinear ODEs, how do you solve them, all those things. And also if you have higher order ODEs, how do you solve them? All these things is like first order ODEs, right? So if you have higher order ODEs, how do you solve them? All these things comes in an advanced course. You can take an advanced numerical methods course to study more about it. But this is where this course ends. So this is what we studied in this course, and I really glad that you guys were able to continue studying this course on to this end, and I also wish you best for your exams. If you have any questions, you can let me know. I will be able to resolve your problems. If not, Um, all the best for your exams, and thank you for this opportunity.
Thank, thank you, sir.
Thank you, Damodar. Thank you.
As I have one doubt, sir.
Sure, sure.
How can
Yes.
we How can we download the previous year assignment questions, sir? Can you tell me, or any other sources can you refer?
So, previous year assignment questions you do not have access to, but some of the questions that I solved in my
Okay.
weeks, all are actually previous year questions. Okay. Uh, most of them are previous year questions, so you can get an idea. But I don't think so. You will be able to, download it. It's basically you cannot access it, I guess.
Okay, sir. So one more question.
Mm-hmm.
Uh, mm, can you tell me the question pattern? It may be 50 questions or something extra questions or 2 mark or 1 mark. Do you know the pattern?
Was the pattern not, you know, in the NPTEL? Were you not able to see?
Yeah, not in pattern, but they given only 75 mark exams and 25 mark for assignment. So we need to score 30% of the
Hmm.
exams.
Right, right.
My 30% in the sense maybe 40 around 40 mark out of 75. But pattern they didn't mention anything.
How many questions is not mentioned, right?
Yeah, that's what I'm asking.
Okay.
Whether it is 50 or more than 50, I don't know exactly. That's what.
Hmm.
Because only 3 hours in all ticket they are the exam duration is 3 hours,
Okay.
so Newton Raphson Newton backward formal it will take at least with the practice it will take 15 minutes or 10 minutes one problem.
Correct,
So
correct.
if it is 50 problem means the time is not sufficient for us, that's what.
Uh, so actually, you no need to worry about it. Um,
Okay.
they will take care of it. They will give you less number of questions if it is going to be very heavy. Okay.
Less number of
Uh,
question means okay, but 50 questions means not even a 20 question we can't solve in 3 hours, that's what I'm asking.
mm, no, I
There
mean
is no pattern.
there is, yeah, yeah, yeah. There is no pattern. I don't see any pattern.
Yeah.
So
If we know the pattern, we can plan according to that, na?
right, right, right.
That's what.
Um, did you try asking the NPTEL regarding this?
No, I didn't ask, sir.
Okay.
I thought that you know. That's what I
Okay.
didn't ask.
Yeah, I
I
mean
think
this.
there
I'm
will be
not
a 2 mark
involved in
questions.
this. Making questions. So that's why I'm not
Okay,
really
okay,
sure. But what you can do is you
okay,
can make a formal request. I will also write to NPTEL if I get to know before the exams. I will.
okay,
I will send. I will post it in the common forum. Okay.
okay,
Uh,
okay, sir.
but you can also post the same question in the common forum. What is the pattern and uh,
Okay, I'll ask.
yeah, yeah. Please do that. So this
And one
guidelines
more.
document does not have.
Ah, that we can see, sir.
Okay. Okay, this does. This has only timelines.
Yeah, timelines only.
Exam pattern. So in I think Sunday, there was one more person who was telling that around 25 questions, 25 1 marks and 32 marks, something like that he was telling. But I don't think
Oh,
that much.
yeah, yeah. One student said that 25 1 mark and 32 mark.
Huh.
So there are 55 questions. So it will not tally 75, na? 25 2 mark, 25
Oh,
1 mark
okay.
means it will
See,
tally.
you no need to worry about it. See that the 75% is about. Did they say it's 75 marks? They just said
Yeah,
75%.
yeah. 75 marks only.
Okay.
It may be 2 mark or 1 mark. I don't know the exact pattern.
Where is that 75 marks?
It's in week 0 or about NPTELs in that I saw in somewhere. Assignment 25 and exam 75. Out of 75, we need to score just 30% of as exam.
Mm-hmm. 1 second, let me check.
The exam format. So just to scroll up. One I saw one exam format heading.
Mm-hmm.
Which one? This one? Exam format. You refer, sir. You
Type
refer
of.
this slide.
Exam. Type of exam compute. Type of exam
On
is
screen.
available here. Okay. It just says online computer based.
Online. That only. But I'm sure about it. 30%, 75 out of 75 mark. But I don't know the pattern only. Okay.
I also saw that some, but it's not coming up here. Does NPTEL online coursework subject to assignment program guidelines, timelines, certification criteria? What should know about final certification exam? Okay, did you check this about the
I'm checking,
exam?
sir.
Okay. So assignment is 25% of average, and proctored exam score 50% of proctor certification score out of 100.
They will convert
That is
into
different. Okay.
that is different, sir.
For us, it is
One more thing, sir.
75%. Yes.
One more thing.
Mm-hmm.
As of now, they didn't release the assignment number 7 answer and 8 answer, and
Oh,
also assignment 8 mark also they didn't release.
okay, really?
Yeah, solution is not released. 7 and 8.
Okay. Solution is not released. Okay. What I
Yeah,
will
yeah,
do
yeah, yeah.
is I will ask NPTEL about it, and if I get any idea about it, I will let you know. Okay.
From your side, you can post it, sir.
Mm-hmm. Yeah, yeah, sure. I will also
Solution
post it in the
also
what do
and
you
also assignment 8 mark is also not released as of now.
I think when is the exam
Up to
actually?
7, coming Saturday. Only two more days left.
Okay, okay.
Not yet released assignment 8 mark as well as assignment 7 and assignment 8 solution is not released as of now.
Sure. I will ask about this.
Okay, sir.
Give me 1 second. Let me write this down. So one is exam pattern,
Yeah.
1 mark and 2 mark. But
Yeah.
you actually no need to worry about it. They will make sure that you will complete it in 2 hours. So that is usually how it will work. So they will not just not give lot of problems. This is a this you are doing it by hand, right? They will understand that.
I saw some video in YouTube, sir.
Mm-hmm.
But last year questions, somewhat assignment questions are repeated now also.
Mm.
So I expect the same for exam also, right?
Sometimes they repeat the assignment questions also. Yeah. And you
That's
can
what.
also
Okay,
go
okay,
through my notes, and some of those questions also may come. Although in my notes I
okay.
would have fully completed, they will ask only like
Yeah,
first
yeah,
iteration value, second iteration value, something like that.
yeah, yeah, yeah. Iteration. Okay, okay. That's I know. That I know.
That is where they
But
will stop.
some different stable like some biggest problem will come now. That's
Mm-hmm.
it will take time now.
Yeah, yeah. So they will take care of that. So they will
Okay.
also solve it, and then they will see whether within 3 hours you can solve it or not.
Yeah, yeah. It's not possible at all. 50
Uh-huh.
question means.
Yeah, yeah. I also know that. So
Assignment 7 and 8
seven and eight.
not solution not released,
Mm.
and also assignment 8 mark also not released as
Okay.
of now.
So mostly it should
There
be
are
coming
three queries.
soon. I will anyway remind them. Okay.
Okay, 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 sir.
Okay. All right then. All the best. Thanks
Thank you,
for
sir.
joining.
Thank you so much for your support.
Yeah, yeah. Thank you
A
very
nice
much.
explanation.
Thanks.
It is
You
very
really
useful
enjoyed.
for us.
Yes, yes. Thank
Thank
you very
you.
much.
Thank you, sir.